Automating Operations.
Hello everyone, this is Socrates Kartakis, an MLOps specialist for AWS. In the last few videos, we covered an introduction to MLOps and we saw the two key pillars of people and processes. In this video, we will cover the technology pillar. My aim is to show you the technology capabilities and principles that you need to follow in order to implement an MLOps platform. That means, after this video, you will be able to implement an MLOps platform by using any tool you prefer. But let's crack on. As a quick recap, we saw the definition of MLOps, that is the combination of people, process, and technologies to productionize machine learning solutions efficiently. Also, we saw the maturity model, and this is what we will follow also in this video. We saw in the initial phase we need to establish an experimentation environment for the data scientists. Then in the repeatable phase we need to move from the world of notebooks to the world of automation and create ML pipelines. Then in the reliable phase we introduce automatic testing and multiple accounts or environments. And lastly we have the scalable phase that we templatize solutions and the infrastructure for the different environments, and we are able to onboard multiple teams and hundreds of ML use cases. And the process and people, as we saw last time, this specific map, we have the platform team, be able to instantiate new environments, the data team that is responsible to prepare the data scientists, they used to experiment in their own environment by creating their own POCs, and then we have the MLOps piece, that we have the model building by creating automation by data scientists and ML engineers, the model testing and deployment, that is a fully autonomous and automatic environment. And lastly, we have the ML governance, that we have a centralized place to store all the models. But let's see how this can be translated to technology. And let's start with the initial phase and the experimentation environment. In the initial phase, what we need to do is to enable the data scientists to experiment. That means that they need to be able to write their own notebooks. Notebooks is nothing else than a list of code, comments, and diagrams that helps the data scientists to experiment. That means that they need somehow to be able from these notebooks to get access to the data. Then by having access to the data scientists use to sample the data, analyze the data, create new features, create the baseline models, and then they're able to evaluate the performance of these models. After that, the data scientists, they continuously improve the models. And in order to achieve that and to track all the experiments, they need also to store and version their code in code repositories. In addition to this, the data scientists, they need to have access to different tools that might be helpful for them. For example, tracking models or changing and preparing data. But how the environment looks like for data scientists? This environment that we see here is just an example of some notebooks. So as we can see at this side, this is how they used to write their code, and to get the output of their code, they need to add diagrams like this one, and they need also to have debug outputs in order to see the performance of their models. As you can imagine, this is not production-ready code. This is just the initial phase, the experimentation phase. But let's move on a little bit to the repeatable phase and how MLOps looks like at this stage. At this stage, what we need to achieve is to move the data science from the world of notebooks to the world of automation. What is the automation that they need to create? They need to create workflows that we call them ML pipelines, that they do pre-processing, training, post-processing, and somewhere they are able to store their models later on to use and productionize them. Before we move to this automation, to the ML pipelines, to these workflows, some steps are required. These steps are mostly related to moving a code that data science used to write without any code quality to a certain quality that is production ready. Let's see the steps that we need to follow in order to achieve that. At the beginning, as we said, we have data scientists that they create their own notebooks. Then in the next phase, that I call it pre-migration code phase, we have the data scientists that they need to prepare their code and to improve the quality of the code by creating functions, by creating specific modules, by creating event tests and error handling. Then the next step is, after we have these notebooks in a certain format, the next step is to move this code into specific repositories. And this is the time that we have data scientists and ML engineers to collaborate together. Later on, we have the data scientists and ML engineers to work on these repositories to create the different ML pipelines. Here I have an example of the code and how it looks like at the beginning before we move to the pre-migration code phase. As you can see, this code example is a mixture of comments, a mixture of outputs, and the code is not structured very well. So somehow, in the pre-migration phase, we need to move to this type of code. This type of code here, as you can see, has organized the code into specific functions that they can operate one specific operation, and also this code has basic error handling that returns exactly the outcome that we prefer. After we have moved into this phase and now our code is readable, our code can be reused, the next step is to start designing our ML pipelines. Here is an example from a computer vision ML pipeline. At the beginning, in most of the computer vision solutions, what we need to do is to get the images, rotate the image, zoom in, zoom out the image, remove the background, then probably do some additional pre-processing, do the data splitting, and then train the different models. As you can imagine, somehow we need to design all these different steps of the pipeline. And these different steps, they have specific inputs, specific logic, and specific outputs. So before we move and before we start shaping the repository and everything, what we need to do is to have data scientists and ML engineers sit down together and design these ML pipelines with simple boxes that they define inputs and outputs. This should be documented somewhere to a Word document, to a wiki page, whatever you prefer. And in order to document that properly, here I have an example of the interface between data scientists and ML engineers. This is a very simple document. This has nothing to do with cloud, but is a very necessary and important step for the whole process. Let's see a little bit the details of this document. At the beginning of this document, what we need to describe is who is the owner, what is this ML use case that we are trying to create, and a quick overview about the objectives that we have with this use case. Then the next piece and the next part is to define the technical details and guidelines. This is mostly some guidelines and some code instructions that the data scientists and ML engineers have co-agreed to follow. How it looks like. For example, here what we have is a theoretical example from a customer that first of all we said that all the different data science and ML engineers will follow PEP8, BLACK, and Sphinx, while they will use PyLint in order to track the testing coverage. But also we had some additional coding requirements. That means that we had functions that they used to perform just one task. We used to avoid global variables, and all the different functions they should be parameterized. That means that we need to avoid any kind of static column names, and more or less to create reusable artifacts. Now, the next step was somehow to structure the repository and to define a clear interface about what the ML engineers and the data scientists used to expect in terms of how they structure the notebooks. Here is an example of how this customer used to structure the notebooks. As you can see, this customer split the different notebooks into different operations. For example, the first notebook is responsible to download data or sample the data. Then we have the exploratory data analysis. Then we have pre-processing and feature engineering, data splitting, the building of a specific image and hyperparameter optimization, and then the deployment and testing and evaluation of the model. And lastly, the cleanup. As you can imagine, this is very, very important structure because later on this can be moved to ML pipelines. The next step is to see how we can structure the actual repositories. In this example here, we have three key main folders. The one folder here at the bottom is the notebooks folder. This notebooks folder contains exactly the code that I described earlier. Then we have another folder, algorithms. In this folder, what we use to store is to store the code for all the different steps of the ML pipelines. In this particular example, we have split the different steps into different step types. For example, pre-processing, training, post-processing. Into pre-processing folder, each pre-processing step should have its own folder, like here, and inside this folder, we need to have a test folder to write all the different unit tests that we want to test, and also a main.py file that indicates that this is what we will run in this particular step. Of course, it is not necessary to have just one file. You can have multiple files, but at least you need a main function for this. If we want to build also custom containers that we will see later on, we need a couple of small files like requirements.txt, image configuration.json file, or you can have a Docker file per step or a global Docker file. After we have defined all the different steps and like pre-processing, training, post-processing steps, the next piece is to link all of them together. So we have this ML pipelines folder, and over there we need only to define all the different ML pipelines that we want to build. For example, here we have a training pipeline and we have two files, the ML pipeline training.py and the input.json. The first file is responsible to define the structure of the ML pipeline, while the input.json is the configuration to this particular file. Then in this repository, we might have also other folders like app infrastructure or test folders that might be responsible for the end-to-end test or for other infrastructure that you need in order to access your models. We can have also some inference pipelines to do batch inference or real-time endpoint code. But this is not the only way to structure an ML solution. Sometimes we can split the code into multiple repositories. For example, here we have two repositories, the model build repository and the model deploy repository. The model build repository should be responsible to host the code for all the steps, the ML pipelines, and the notebooks, while the model deploy repository is mostly the code that we need to use in order to deploy a model into production. We have two different types of models that we want to support. The one is based on real time and the other one based on batch use cases. In real time, what we need to do is to create a server to host the model, and then this model needs to get the requests and reply back immediately. The request is just a single row of data, and the outcome is a probability. In the batch use cases, what we need to do most of the times is to indicate a location on the cloud that we store a batch of data. Then we need the model to get access to this data, perform all the different predictions, that means multiple predictions, and return back the results into the same place. This is the difference, and this is why we need also the model deploy repository to define all these different solutions, and including also some additional tests that we will see in the next few slides. But the key question is, how do we structure an ML project in order to productionize everything? Here is an example of the two repositories that I mentioned earlier, the model build and the model deploy, and how everything is linked together with CI/CD pipelines. In the model build repository, what we have is the data scientists and ML engineers to collaborate. Let's say that they already have some example code, they already have implemented an ML pipeline, and we need to just add a new step. How? We need to create a feature branch, we add this new step, and then after we're ready, we have tested that, we need to push the changes to the main branch. By merging with the main branch, this will activate a CI/CD pipeline. The CI/CD pipeline will get the code, run some validations, run the different unit tests that we have, and then create custom containers if it is necessary. And then it will deploy the ML pipelines and it will start the execution. By starting the execution, this will run all the different pre-processing steps, training, post-processing steps, and more or less it will produce a model. Well, what we used to do is to store all the different versions of the models in some place that we call it model registry. Model registry is one of the most important capabilities that we need to have in MLOps space. Why? Because it is the single place of truth that we store all the models, all the different versions, all the metadata. We store metadata in terms of the KPIs, precision, recall, etc., or in terms of where we have the data, the lineage of the data, or we store metadata related to who has done different actions to this particular model. For example, who is the one who created this model? And we are able also to store the container that we will use to train a particular model in order to use exactly the same container while we deploy this model. And now that I'm talking about deployment, the second piece is about having a model deploy repository. In this model deploy repository, as we saw earlier, we store the code of the real-time endpoint, as we call a server that hosts the model and it gets requests, or batch inference, for example. And also it stores the code of the configuration of this setup, or even the different tests that we need to run. How do we trigger the model deployment? And how do we trigger a CI/CD pipeline like this? We need to trigger that from the model registry. We have some approvers that they need to go to the model registry, select the right model, for example, model version 3, and then trigger the productionization piece that will trigger a CI/CD pipeline. This CI/CD pipeline, the model deploy CI/CD pipeline, will get the code from the model deploy repository. It will deploy, for example, the real-time endpoint. It will run the different tests, and then it will wait for some manual approvals. Then after the approval, what we need to do is to deploy this solution into production. And this is the complete story. This is how we need to structure the different repositories, CI/CD pipelines, and model registry in order to have a production-ready solution. Quick note, we have different ways to set up our solutions as we saw earlier. You can have one repository that has all the code for model build and model deploy, and a very long CI/CD pipeline that gets the code through all the different environments of development, pre-production, and production that we will see later. And we can have two different repositories, one for model build and one for model deploy. What is the difference between the two? In a single repository, this is very good whenever we want to productionize, let's say, the training and the batch solution. Or whenever we have batch use cases that the same pre-processing steps like the training can be part also of the batch solution. That means we do pre-processing, training, post-processing, and we do pre-processing, batch inference, and post-processing. In the case of the two repositories, this gives us more flexibility on the deployment piece. That means that we decouple the model training and building from model deployment. And this is very, very important because in order to deploy a new version of the model, or in order to deploy the same version of the model but with different configuration, we don't need to retrain. And we have seen also another solution that we have three repositories: model build, model deploy, and model monitoring. And this is mostly because we want not only to decouple the model build from model deploy process, but also the monitoring is a separate process that can run in a different frequency. The number of repositories more or less indicates the number of the CI/CD pipelines that we need. That means also the more repositories that we have, the more flexibility that we have, but the less repository we have, it is easier to maintain the whole solution. Now, we have standardized the way that we have structured the repositories, the number of repositories. The next step is also to standardize the way that we store our data. Each ML pipeline will run pre-processing, training, post-processing. So somehow we need to be able to audit all the different executions. Here I have an example from a real customer story. In this example, we know that the data is somewhere on the cloud, right? Like the input data here. And then for each ML pipeline, for each ML use case, we create a subfolder. Into this subfolder, we store all the different executions. Here, it is a different folder with build ID. This build ID might be the timestamp of the execution plus the Git hash. With that way, you will be able, let's say, to say and to query your system and to say, give me all the executions of last Monday between 9 a.m. and 3 p.m. And what do we store into these subfolders of executions? We store the input data, all the outputs of all the different steps that we execute in the ML pipelines and the code that we used in order to build these ML pipelines. Some quick notes here. At this point, we have this input folder here. For some customers, what we used to do is to copy the input data from here into this folder. This is valid when the customers used to go and change the historical data. Okay, that means, for example, if you have your customers' demographic data and they change the address, they can go and change the historical data. With that way, we will lose the lineage of the data and what data we used in order to train this particular model during this execution of the ML pipeline. Now, of course, if the customer does not have the ability to change the data, then we can have just a reference point to this data. Up to this point, in the initial phase, what we saw is that the data scientists, they need their own experimentation environment in order to create their notebooks and their POCs. By moving from initial phase to the repeatable phase, we have a more complex environment, a little bit. Why is that? Because now we start moving to the production. We start moving to the core MLOps piece. Let's see the different parts. At the lower level, we have the kingdom of the data engineers. Data engineers, they ingest the data on the cloud, they prepare the data, catalog the data, and more or less they create the historical data that the data scientists used to need in order to create their POCs into the experimentation environment. So we have the first collaboration between data scientists and data engineers. The data engineers, after they prepare the data, they move them as a snapshot into the experimentation environment, and then the data scientists, they create their notebooks, their baseline and best models, let's say, and then at some point they are ready to assess the solution with the lead data scientist. What do they assess? They want to make sure that this solution can be generalized and the model can generalize and can be used in order to solve a business problem. After this assessment, the lead data scientist might approve or reject the solution. If the lead data scientist approves the solution, then what we need is to provision a new set of repositories, like we see here, and a set of CI/CD pipelines that will be for our production-ready solution. The data scientists, together with ML engineers, they work on these repositories, the model build, model deploy repositories that we saw earlier, for example. Then, by merging with the main branch, what we saw is the CI/CD pipeline will get the code and it will deploy the ML pipelines to a separate environment that we call it development environment. This development environment is the beginning of the production environment. Why is that? Because at this environment we have data coming in from the data lake that is production-ready data, the full set of data, the full scale of data that we need in order to perform pre-processing, training, and post-processing. Now, some quick notes here. The experimentation environment and the dev environment, we have them separate here. Why is that? Because what we want to make sure with the experimentation environment is that the data scientists, they have the flexibility to play with new libraries or try new research techniques and more or less have access to break things. While the development environment that we have here is more or less a production environment that nobody has access to do manual operations. Everything should happen through CI/CD pipelines and by committing code to repositories. And it is an environment that we store real data. That means no one needs to have access to there. Now, if in experimentation environment and the development environment we have exactly the same policies in terms of data access or service access, then we can consolidate these two environments together. At the top layer, I have introduced another environment, the tooling or automation environment. In this environment, we need to store all the different code artifacts and model artifacts. And this is the place that we store also model registry. In model registry, we store, as we said earlier, all the different model artifacts, metadata, and the containers that we used in order to train these models in order to use the same containers to deploy into production. And this is the repeatable phase. What we have achieved to create a repeatable process based on ML pipelines and everything driven by using standard repositories, repository structure, and input and outputs. Now, after this repeatable phase, we have the reliable phase. In the reliable phase, we need to introduce the model testing and model deployment, and also to improve the model governance. Let's see how it looks like. This is the architecture of the repeatable phase. The next step is to start introducing an environment of the pre-production staging or testing. You can use any name you prefer. In this pre-production environment, what we need to do is to begin the productionization of a model artifact. That means from the model registry, these approvers, they are responsible to approve which model will go to production. This will trigger a process through CI/CD pipeline that will get the model from the model registry. It will deploy into the pre-production environment, and it will start running the different automatic tests. So the approvers, they play key role here. Of course, you can remove the manual approval gate and every model that you produce to send it to production, but we don't recommend this. What are the tests that we need to run? The first type of test that we need to run is unit test. Unit test is to check the logic. And by the way, the one who is responsible to write the logic is the one who is responsible to create also the tests for the logic. Even if it is weird, the data scientists should be responsible to write unit tests. At the beginning, this might not be possible. That's why we need the data scientists to collaborate with the ML engineers to improve the testing coverage, and also the ML engineers used to upskill the data scientists in order to write this better code and the tests. The next test that we need to run is about integration test. Integration test, more or less, we need to answer a simple question. Does the inference part works? Yes or no? If we have a real-time use case and we have the server that we host our model, if I send a request, does it return results back? Yes or no? With the batch inference, exactly the same process. The next test that we need to run, most of the times, is about stress test. This is, for example, if I send to my server 1 million requests to get predictions back, is that going to work? So we test mostly the edge cases. And the next test that we need to run is about the end-to-end test. The end-to-end test, let's say that you have a server, and in order to access the model, before the server, we have another service like an API gateway or a Lambda function that triggers the model into the server and gets the results back. So we need to test the end-to-end logic, the end-to-end integration with the different services. After we have completed everything with the pre-production environment and we have run all the different automatic tests, the next piece is to introduce production environment. What is the flow now to move everything into production? We need more or less to have the approvers and another manual approval gate here to go and approve, check the tests first, check the results, and approve that this model will go to production. After they approve everything by using CI/CD pipelines and the approval gates there, then we have the CI/CD pipeline to continue and to deploy the solution into production. But we can use this solution from all the other applications. But in production, we need also to run some specific tests or some specific monitoring or other processes in order to make sure that everything is robust and everything works, in order to avoid any timeouts, any problems by serving our models. What do we need to run into production? First of all, we need to have deployment guardrails. If you are familiar with that, we can support blue, green, or canary deployment, that we can take that in another video and to deep dive on this. Or other deployment methods in order to make sure that the functionality works, and if it does not work, then to support automatic rollback. The next piece that we need to run is about data and model monitoring. That means somehow we need to check if, let's say, the data that we use to train the model and the data that we are getting in order to make predictions, they follow similar behavior. Similarly, we need to do the same for the outputs. not only for the input data, but for the predictions or the ground truth. We will take that also in another video. For some other customers, we need also to run some A/B tests. What is the A/B test? An A/B test is we split the traffic between two variations of the same model, the new version and the old version. And we start checking if the new model performs with the way that we're expecting. And then slowly we transition from the old model to the new one. But sometimes we might need to run more extensive tests. That means that we can have two different variations of the same model, the new and the old, and the new one to be like a shadow variation. In both these variations of the model, we send exactly the same traffic of requests, but the difference is we serve the customers with the old model and we store the shadow variant results into a separate environment, in a separate storage, let's say, that the data scientists or ML engineers can go and run the different tests and hypothesis tests, etc. Up to this point, what we have covered is just the basics of MLOps. And more or less what we have seen is how one team can start productionizing solutions. Let's see how the platform team can help us in order to onboard new teams and what we need to create in order to achieve that. So we need to move from the reliable phase that we saw earlier to the scalable phase. In the scalable phase, more or less what we do is we templatize the infrastructure code for all these environments in the middle, from experimentation, dev, pre-prod, and prod. And then we give this infrastructure code into the platform team, into a separate account that we might call it Advanced Analytics Governance account. And then the platform team is responsible to create new environments for the new team. And they are responsible to use exactly the same code in order to instantiate the infrastructure for all these environments. This is extremely helpful for big customers that they need to ensure that all the different teams, they use exactly the same security measures, exactly the same infrastructure, and they are not going to have security breaches or other issues. Why do we need to create all these different environments? Someone might say that this is a big overhead. The reason of doing that is because we need to, at some point, achieve isolation in terms of teams, data, and owners. For example, let's imagine that we have two different teams. One team is responsible for churn prediction, another team is responsible for predictive maintenance. These two teams, they need to have isolation of data. We cannot have a team of data scientists that they do predictive maintenance to have access to financial data. This might breach a lot of privacy, data privacy, or other issues. So, in that case, we need to create a new set of environments for a new team. But when do we create a new environment for some use cases? Let's imagine that we have a new use case. What we need to assess is, for this use case, do we have the team to have access to the same data that they already have for other use cases? Do we have the same team that delivers this solution? And do we have the same product owner responsible for this solution and to pay for this solution? If we have a yes answer to all these questions, then we host this ML use case into an existing set of environments. If we have now a no answer into one of these questions, then we need to create a new set of dev, pre-prod, prod environments and to have the use case into this environment. That means that we don't need a separate set of environments per use case, but more or less what we suggest to our customers is to have one set of environments per business unit. So if we have 10 teams, most of the times we need 10 of these sets of environments. That is manageable. What is the next step? Let's see how we can integrate the world of MLOps to the world of the data lake. Normally, whenever we have a data lake, what we used to do is to ingest data from on-premise system on the cloud into a landing or raw bucket. And then what we have is ETL pipelines that they get the data, audit the data, catalog the data, and store the data to a provision bucket in the provision storage environment. And then what we have is other ETL flows that they need to create the historical data. Let's see what data do we need per environment, the development environment, pre-production, and production environment. In the development environment, as we split that earlier, what we need to achieve is to train the different models by creating the different steps and ML pipelines. In that case, we need just historical data that we will be able to train the models. In pre-production environment, what we said is we need just to test the models. That means over there we need just test data or some data for batch inference. Then in production environment, what we need is just data, batch inference data, that they come and the batch inference pipelines, they are able to get the data and return the results back. But this is the case of batch use cases. What if we have real-time use cases? If we have real-time use cases, most of the times the data will land to the model from an API call. Then we will trigger a server and we will get the results back from the API as well. That means that we don't need even to have this data here. And this is more or less how we integrate the two worlds together. But let's see what we have presented so far. We presented all the different capabilities from the platform team, data science that they do experimentation, the MLOps piece of model build, test and deploy, and the model governance piece. And more or less we land into this architecture design. The key idea here is to use this architecture design as a skeleton. And more or less we describe today the technology principles and capabilities that you need in order to build an MLOps platform. How you will do that and the tools that you will use, it's up to you. In the next video, I will deep dive how you can implement everything by using AWS services. So, what we covered today was just a quick summary of what we saw in the previous videos. Then we focused on the technology pillar, but with an abstracted way. That means that we checked just the principles and the capabilities that you need in order to build an MLOps platform without necessarily focusing on the services that you need. And we saw very briefly how we can integrate the world of MLOps with the world of the data lakes. In the next few videos, we will deep dive on how you can implement an MLOps platform on AWS. Until then, stay tuned.